Welcome to T2 Day 2 of Honors Precalculus. Today we're going to do and work with graphs of composite trig functions. Let's warm up with remembering what the absolute value function does to graphs. So if we were to graph y equals x squared minus 9, for example, y equals x squared minus 9, it would cross here at -3 and +3, and it would go up like this, and it would go up like this, and it would cross all the way down pretty far down at -9 and go back up, and my curve is pretty terrible here. My curve is pretty terrible. This should be a lot steeper. So it goes all the way down to -9 and comes back up. But the absolute value means you take all the y values that are negative and make them positive. So this part right here, what's below the x-axis, gets flipped up. So what does this graph actually look like when you're done? It goes all the way up to 9 like this. It's the flip like this. So when you're done, the final graph would just be the red, not the green. Similarly, if we graph sine of x, well, in this case, 3 absolute value sine of x. First, we graph 3 sine of x. We know sine starts here. It's going to go up to 3, back down to pi. It's going to go down to 3 and back up to here. And if you keep on doing this and graphing 3 sine of x, here's what you end up with. You end up with a very familiar, just stretched out sine function. But again, if you were to take the absolute value of this, it takes everything that's below, so you would take this curve right here, this one right here, and this one right here, and you would flip them up. So what do you end up with? You end up with something like this. It looks like these mountains going up and down, these nice curves that I'm kind of botching a little bit. But you take everything below the x-axis and flip it above it. So if we were to graph the inner function here, 4 cosine pi over 2x plus 3, the midline is going to be at 3 right here. And then it's going to go all the way up to 7 because it goes up 4. It goes up to 7, there's 3, and it goes down to what, -1, right? Because you got to go down 4, so you're going to go down to -1 here. And what are you going to end up with? It's going to start all the way up here, and in this case, the period is going to be 2 pi divided by the b value, which is pi over 2. So in this case, the period is going to be 4. So it's going to repeat every 4. So it's going to get back up here at 4. So it means it's going to be down here at 2. So what does this look like? Well, it's going to be halfway here and here. So if we do one curve right here, it's going to go back up like this. And then you're going to do the same thing all the way to 8. So remember, it goes down to here. It's going to be here and here. We do the same thing over and over again. So this is without the absolute value or the negative sign, but I'll keep on graphing the rest. You end up with just the inner function here. But then what's going to happen is all the things are going to be flipped because it's everything below will be flipped above, but then the whole thing will be flipped below. So what that means first that happens is because of the absolute value, everything below will get flipped above, but then the negative sign will flip it below. And then everything above will just get flipped below. So in this case, what happens is the green gets flipped above and then back, but then all the blue gets flipped over. So all of these right here, everything that's above right here, everything that's above is gonna get flipped down below because of the negative sign, and the green is gonna end up staying put. So what do you end up with? You end up with the red. So all of this blue just gets flipped down below because of this negative sign. So you end up with this repeated over and over again. I recommend using the copy paste feature. So you got to do this carefully. So let's look at this cool function, which is 0.5x plus sine of x. We know that this part right here it goes between -1 and 1. That's as small and as big as it gets, but 0.5x can get really big in either direction. You can plug in a negative infinity or a positive infinity. So between what two lines does this oscillate? Well, sine of x is going to either at most change this by 1 or go down by 1. So it's either going to go up 1 or down 1. So what that means is it's going to be upper bound will be 0.5x plus 1, and the lower bound would be 0.5x minus 1, because no matter what x is, sine of x at most can add 1, and at worst can take out 1. I don't want to say worst, but could at most take away at most 1. So in the sheets, when it says use converge, what I'd like you to do is just use Desmos. And if you use Desmos to graph this, you graph the two lines 0.5x and 0.5x plus 1, and it'll be something like this. And you'll do, so that's y equals 1/2 x plus 1. And if you graph y equals 1/2 x minus 1, you end up like this. And then what you end up with, if you graph the function, let's say remember it's 1/2 x plus sine of x, keep it in radians, that'll be helpful. You end up with this really cool function that does like this. It oscillates in between these two things. It's really cool. So the final function touches the red and blue and stays in between them. So we can make these more complicated. We can multiply a sine or cosine function times a polynomial like this and see what happens. Sine and cosine are very limited, so it actually makes really cool, really fun shaped graphs. So if you figure out and fill in this table, here's what you get. You get these values, and they don't seem to help too much. Like, what does this mean? It doesn't look like anything you've seen before. This doesn't seem to be a nice pattern to it. What's really interesting, though, is if you graph the pieces, it becomes apparent what's going on. X squared plus 1 is going to be the upper bound here. So what does x squared plus 1 look like? It crosses here, and it's going to go up, vaguely like this and like this. And then if you flip it over, it'll go the opposite direction like this and like this. And if you plot these points, if you plot the individual points, what's interesting here is you get something that looks like this really cool oscillation. So what's going on is sine, no matter what you plug in, is oscillating between -1 and 1. The biggest thing it can be is 1, and the smallest thing it can be is -1. And then it's going to be multiplied by this function. So what ends up happening is you end up oscillating between the positive and negative versions of, you have x squared plus 1, and you have y is equal to -x squared plus 1. It's super cool. And we just said it's going to oscillate between the upper function of x squared plus 1 and the lower function of -x squared plus 1. And it doesn't seem apparent when you make the table, but then when you graph it, you'll notice that it gets stuck between the two and it keeps oscillating. Again, it's because no matter what you plug in for sine, the biggest thing you can be is 1 and the smallest thing is -1. So you're multiplying x squared plus 1 by decimals between -1 and 1, and it just oscillates, so it gets pulled apart. It's pretty cool. So this one has cosine of pi x. So cosine of pi x, and it's being multiplied by this function. If you just graphed 8 times 0.5 to the x, if you did 8 times 0.5 to the x, plug in 0, start it up here at 8, because 0.5 to the 0 is 1. Plug in 1, so it's 1 is going to be 4, and then 2, it's going to go half again, so 2, 2. So what you end up with, 3, it's going to be here. So you end up with a roof like this. And then on the other side of it, because cosine also oscillates between negative and +1, you end up with a floor, that's the word I was looking for, a floor that looks like this. So it goes halfway again. So you have a floor that looks like this. But cosine is going to be pulled apart in between those things. So what you know, though, is when is this going to be 0? It's going to be 0 at all at 1/2. So for example, cosine of pi x, when x is 1/2, you know, with cosine of pi over 2, which is 0. So when x is half, it's going to be 0, and 0 times this is 0. And then the period is going to be every 1, because if you plug in, if x is 3, 3, not pi over 2, 3, you end up with cosine, I meant 3 over 2. So you have cosine of 3 pi over 2, which is again just 0. So that's where all these zeros come into play right here, the zeros that I'm plotting here. So that's where it crosses. And we know that cosine starts all the way at the top here. So because cosine of 0 is 1. So what ends up happening is this drops down, then it goes back up, and then it drops down, it goes back up, it drops down. So it's stuck between these things. So it's going to go down and then go back up. It gets bigger because this ends up going out. So you can take a cosine function that you know and then stretch it in really fun ways. So the technical term that you're going to see is dampening factor. The dampening factor is this right here, 8 times 1/2 to the x. That's the dampening factor. And when does the dampening occur? When does it get smaller? As x goes to infinity. So you plot the zeros and then stretch out the curves and graph them as smoothly as you can. They're really steep, so it's hard. And if you get stuck on these, use Desmos. It's really fun. You can change the colors of all these mins and maxes and the colors of the function themselves. And we've talked about this before, that since sine and cosine are periodic, they repeat themselves infinitely. So we know that the period is 2 pi, meaning you can shift them to the left and right 2 pi. So theoretically, you could write this as sine of x plus 4 pi, which is going to be the same as sine of x plus 6 pi. And you can do the same thing for cosine. So it's going to be cosine of x plus 4 pi. It's going to be cosine of x plus 6 pi. You can arbitrarily add 2 pi. So then in general, if a function is periodic with a period of k, then you can say the function is also equal to the function plus k times, sorry, k is not the period. The period is right there, PD, or k is an integer. So any integer multiple. So for example, as we saw above, we know that sine of x, the period is 2 pi. So we can say that if f of x is sine of x, we know it's also going to be f of x plus 2 pi times k, where it's any integer. So you can make it any integer inside here. So x can be x plus 2 pi k. So you can turn that into x plus 2 pi times any integer, 17. Or x plus 2 pi times a billion. It doesn't matter. You can shift it left and right as many multiples of 2 pi as you want. The x right there. So the way they have you prove that things are periodic algebraically is based on what I just told you above. You know that f of x plus, because it's sine, it's 2 pi k, is going to be equal to the function sine of x plus 2 pi k squared. That's what this function is defined as. But we know that f of x plus 2 pi k is going to be equal to sine of x squared. It's another truth we know, which is definitely going to be equal to f of x, because by definition, this is what we were given right here. So basically what we know is that because you can slide it infinitely over, the squaring doesn't change anything. So similarly over with cosine, any periodic function raised to a power, with the similar algebra will end up with itself. So you can move it over. So basically you can shift it over, and then you can shift it back, and then it equals back with what you started with. We will definitely talk about this more in class. Another way to see this is it shows that moving it over 2 pi k, even if you do that, you end up back at f of x, which is the definition of periodic. So then you have a definition at the end when you say a function is called sinusoidal if it can be modeled by a function of the form a sine b x minus c. We've worked with that definition before. A cosine curve can also be modeled by a horizontal shift of the sine curve. So you can model all sine functions with cosine and vice versa. So we just pick sinusoidal as our base, sinusoidal. So on your calculator, you'll see sine reg. So sine is the base trig function we use. So it tells us that if y1 is one function and y2 is this function, it gives us a really cool result, which is if you add them together, you still get a sinusoidal function. So if you have two sinusoidal functions, you can add them together, you get one function plus another. It's also sinusoidal with period 2 pi over b. The key is that you're working with sine in both cases, which has a period of 2 pi.